Welcome to chapter 5 lecture. Today I want to start part A, and we'll come back again in part B. Chapter 5 is on thermochemistry, and thermochemistry is the study of chemical reaction and the or energy heat energy associated with it. Let me share my screen. I want to share my screen as usual. You will be following the lecture proceeding, writing down the key terms and probably maybe making your role known. Let's see, chapter 5 is on thermochemistry, and thermochemistry is simply the study of chemical reactions and the energy that involve heat. In chapter 1, we define energy. By now, you should be able to define energy, know the main form of energy, kinetic energy and potential energy. In chapter 1, you learn how to solve the kinetic energy of an object, right? Expressing the energy with the correct units, the SI unit, which is the joules. We'll see again in chapter 5. Well, thermochemistry is a branch of thermodynamics. All right. In Chem 2, you will cover in details thermodynamics, but this is just an intro. And when you get to Chem 2, you will be required to recall some of the concepts we will go over today. All right. On my PowerPoint slides, I've broken the chapter into two. All right. Part A will go over section 5.1, 5.2, first law of thermodynamics, which is basically the conservation of energy. Energy cannot be created or destroyed. That's basically the first law of thermodynamics. There are three laws. The two laws are left, that is for Gen Chem 2. Section 5.3 will look at the enthalpy of reaction, which is basically the heat of reaction, enthalpies of reaction. We will look at the calorimetry, how to measure the heat of reaction in the lab, and in part B, we will look at the Hess's law, enthalpies of formation of compounds, bond enthalpies, and the energy value of food we consume. That's the last thing we look at in section 5.9. So as usual, please have a piece of paper somewhere to write your notes. Let's see, in 5.1, we will look at the nature of energy. Remember, energy is, all right, energy is simply the ability to do work. All right. Sometimes this is defined as the capacity to do work. It still means the same thing. There are two most important types of energies: kinetic energy, all right, which we looked at earlier on, kinetic energy, and PE for potential energy. These are the two most important energies you need to remember. Okay, this was chapter 1, which we define energy: ability or capacity to do work or transfer heat. In this chapter, that is chapter 5. Chapter 5 is about thermodynamics, which is simply the study of energy and its transformation. Okay, transformation, energy can be transformed or from one form to the other form. It could be from potential energy to kinetic energy. It could be from chemical energy to heat energy and so forth. The study of the transformation, okay? The study of the transformation of energy is a branch or is the subject of thermodynamics. A branch of thermodynamics, which is now chapter 5, thermochemistry is the study of chemical reactions and the energy changes that involve heat, right? Some chemical reaction, they release heat to the environment. Some chemical reaction, they absorb heat from the environment. The study of those chemical reaction is what we call thermochemistry. Well, I'm not going to go in details or require you learn about the potential energy, electron potential energy, which is just a energy associated with two charges are attracting one another, the positive and negative. When they are far apart, right? When they are far apart, they don't feel anything. That means the electron potential or energy is greater than if it is too close. Then we talk about the negative. I won't require you to calculate the electropotential, the electrostatic potential energy for two charged particles. I leave that, but what I want you to remember is the SI unit for energy. All right, energy is joules, which is simply abbreviated J. And this unit here, this is from the potential, I mean kinetic energy. Recall, kinetic energy is determined by multiplying the mass of an object times the velocity square, where m, where m is mass. All right, let's see here. When we say where m equals to mass in kg and v is velocity, or this sometimes speed in meters per second, so that when you square, you see this, when you square velocity here, you end up with meter square. And this unit here is the same as 1 joule. That was chapter 1 concept. So you need to recall that. You need to recall that. Let's see, this just what happened when positive, negative, or charged particle attract, that energy is given off during the bond formation. We'll see that later on, that when a chemical bond is formed, energy is released, and it is negative. You're gonna see anything less than 0 is negative, anything greater than 0 is positive. When the ions are far apart, there is no chemical bond formed, there is no energy given off, therefore the bond does not exist for electrostatic attraction between two particles. Now, that is just an overview of definition of an energy, okay? You need to, or you should be able to define energy. You will see that in the quiz or in the exam, capacity to do work. Please read more on section 5.1. Let's look at 5.2, the first law of thermodynamics, okay? First law of thermodynamics is simply the law of energy, what? Energy conservation. That means to conserve energy. And it states, all right, states that energy cannot be created, all right, created or nor destroyed. All right, you'll never destroy, you'll never create energy, but you can transform from one form to the other form. That is just the first law of thermodynamics. As I said, there are three. I will leave two. You will cover in Chem 2. In general Chem 2, you will look at the other laws of thermodynamics. Energy can be converted from one form to another, but it cannot be created or destroyed. That's just the law of conservation of energy. Remember, there was the law of mass conservation. Matter cannot be created or destroyed. But here, we are talking about energy, all right? Cannot be created or destroyed. So if you know how to define the law of mass conservation, you should be able also to define the first law of thermodynamics. So if you remember or you think about some experience you may have encountered in real life, such as heating of your home, it involves transformation of energy, okay? Generation of electricity, flow of electron. How do we start off from there? It has to do with some chemicals reaction somewhere, which is converted into heat. I can give you another example which illustrates the first law of thermodynamics, gasoline. We all know gasoline, right? Gasoline has stored energy in the chemical bonds. And when those chemical bonds, all right, are either broken or the stored energy in the chemical bonds are converted into other forms of energy. For example, mechanical energy to move the internal part of the engine, okay? It could be converted into heat energy, right? To warm your car. It can be converted into light energy for the headlamps, or even sound energy for your stereo in the car. We can just illustrate example on how the law of mass conservation to show how energy is conserved. Another example is sunlight, all right? Is converted to chemical energy in green plants during photosynthesis. There are many more examples of conservation of energy, conservation of energy. Okay, so remember, take home message from here is you should be able to define the first law of thermodynamics. Now let's see, in order to illustrate the conservation of energy, chemists always are interested in what we call the system. Look at what is called the system, and I'm going to use a diagram. All right, I'm going to use a diagram to show you, all right, to show you what system is, all right, with respect to the surrounding and what we call the universe. So if I have a diagram here, this is where the reaction is taking place. You see here, we have A plus B going to C plus D. This is where the reaction is taking place here. Assume that this is the reaction flask in the lab, or maybe a beaker in the lab where you put two reagents together and either the heat is given off or heat is absorbed from outside, from the lab. So in this case, we call this the system. That is where the reagents are. And outside, all right, here, what surround the system we call here surrounding. You can think of it as in the lab is the surrounding, it surrounds the system. So underline or know, or in the future, moving forward, when we talk about the system, think of the area of interest. The rest is just what we call the surrounding, or we call sometimes environment. Uh, there is an equation here which you need to know that when we have what we call the universe equals to the surrounding, all right, surrounding plus the system. Sometimes we abbreviate this as uni equals to SRR plus SYS for the system, SYS for the system. So know what is definition star portion of the universe. So when we say universe here, look at the word universe. The universe is everything. We single out to study the system. Remember what I said here, that chemists are interested in the system. That is where the reaction is taking place. Is using an example of hydrogen and oxygen, all right? In this reaction, let me just blow up this so that you can see. In this reaction between oxygen gas and a hydrogen gas, we call the system, all right? We call the system. This is our point of interest. The surrounding are everything here, the cylinder, the piston, and everything, all right? That constitute what we call the surrounding. Okay, not the surrounding. I would like to use this for obvious reason. I'm going to show you what we mean by a closed system. There are three types of systems, all right? Here, types of systems. There are three types of system. One, all right, one, there is the open system. There is the closed system, and there is the isolated system. All right. In order to differentiate the three types of system, there are two things you need to compare, all right, in each of the three systems. And these are two things, matter and energy, all right? Energy, which could be in form of heat, all right? It can be in form of heat. So I'm just going to look at this matter and energy. And to divide those three in form of the system, open system, a region of the universe being studied that can exchange heat and mass, all right, with the surrounding. Example is if you have H2O here, if you boil just water, it will be able to do it, to lose mass. Let's say just we have hot water, so hot enough that it can evaporate, it can vaporize, it can change to gaseous state. So if it changes, because the container is open, we are losing both heat and mass. We call that an open system, an open system. There is the closed system. In this case, for closed system, we have, let's say we have our H2O here, all right? Let's say hot H2O, which we can lose, hot H2O in a closed container, but it can radiate, it will lose heat, okay? A region of the universe being studied that can only exchange heat. So underline the word heat, but we cannot lose mass. And then this is number one, this is number two, And then if we have the same container, but in this case, in some insulation, all right? If we insulate these so that we do not do it, we do not lose both heat and mass, we call it a closed or isolated. So here is, all right, here is open. So I'll call this open. I'll call this closed system, and this is isolated. What isolated system? We call this isolated system. So there are three systems. You should be able to explain, or if we are given an example, a case study, you should be able to identify whether it is open, whether it's closed, or whether it is isolated. Isolated is a region of the universe that cannot exchange either what heat energy or mass with the surrounding. Let's see, the learning check here: is a human being an isolated, closed, or open system? All right. The correct answer for that is it is an open system. All right. It is an open system because it loses both heat to the surrounding. All right, and it loses both heat and mass. It loses both heat and mass. So we call that the open system. That is an open system, right? Human being is an open system because it loses. So that is open system. Why? It's open system because if you hold somebody, you cannot feel heat, right? That means it's giving away heat. If you sweat, all right, you're losing mass. So we consider that as open system. Look at more example in the text on types or classifying different system as either closed or open or isolated. Now let's see, shift gears to what we call internal energy of the system. In this case, we are talking about internal energy of the system, which is the sum of kinetic energy and potential energy. All right. When we talk about the internal energy, sum of kinetic energy of molecule or atoms of the system plus the potential energies. We denote internal energy using this symbol. It's a thermodynamic term represented by E, all right? This means, so that you get to understand down the line, this means change. It's understood to mean change in internal energy of the system, internal energy of the system. This means change. All right, it means change. We call that delta. All right, remember this is delta, which means change. We denote that. So delta E means change in internal energy of the system. Okay, we use, or we only look at the final and the initial ways it's starting, ending, and depending on the sign of change in internal energy, either the system is giving away heat energy, or either the system is absorbing heat. Let's see, in the formation of H2O, when hydrogen gas react with oxygen gas to form water molecule in liquid state, all right? In liquid state, if you look at where we are starting, this is the final, all right? If it is combining, the change in internal energy is less than 0, which means it's negative. Delta E less than 0, this means it's negative what? This means negative value. Remember the number line? But if we go on the other side, final minus initial. The final, which is lower than the initial final, we end up with a negative value. You have to understand what this means. Means it's a negative value. If change in internal energy is greater than 0, means final is greater than initial, energy is absorbed. So here we say energy is released. That means it's given up when it is negative. Energy is absorbed when it is positive. Here, energy is lost to the surrounding when it is on the negative territory. If you look at here, let's say here is 0, negative delta G is given off, but when it is positive, we say that energy is absorbed. We will not calculate that, but remember the sign convention for that. Let's see 3 things we need to understand as far as thermodynamic quantities are concerned. There are 3 parts: either number, all right, a unit, and a sign associated with it. For example, unit I gave you earlier on, joules, okay? And a sign, it could be either positive or negative. What do they mean? And of course, we have a number, 58 compared to 198. It's just the magnitude. Let's see here. Note about the sign, positive delta E, that is positive change in internal energy, results when the system gain energy from the surrounding. Okay, remember surrounding? Remember the system? Let me go back from here to my diagram right here, so that when we say energy is coming in, all right, it is coming in. I use different color. This means it is gaining from the surrounding. It is losing to the surrounding, okay? Let's keep an eye on our diagram to really nail down the sign convention for the thermodynamics. Change in negative means it's losing. The system is losing, okay? The system is losing. Now, there are, when energy is exchanged between the system and the surrounding, it's either exchanged as heat. And by the way, heat is used. This is what we use in. Heat. We use this Q, means heat, and work. We'll use. Of course, we know W, the first letter for work. W did not work, but what you need to understand is Q. Whatever we are looking at thermodynamics, thermochemistry, Q means heat. Either heat is given off, it is absorbed, work is done by the system, and I'm not going to go in details into this, but it's better to have this diagram here. Learn until you can reproduce. If you look at what is happening here, this is our system, the yellow on the diagram here. This is the system, and the black box or container is the surrounding or the environment. Here, Q is negative Q. This one here is positive Q. If heat is getting into the system, is positive. You are adding something in. It's getting into the system. So we can miss it when you have it here. Q greater than 0. I don't want to, when you see this symbol, please don't ignore. I like to use my notation on the whiteboard. You see, getting into the system means positive. Anything greater than 0 is positive. But if you look at the something getting out, that means it's less than negative. Therefore, if it's getting out of the system, we use an arrow. The arrows will help you commit to your memory where the heat is going. Is it coming out of the system or is it getting into the system? Anything getting out is negative. You are subtracting. Anything getting into the system, you are adding. So this is the notation which will represent this. Now, as far as the work is concerned, if it is getting into the system, we are adding W, and that is why here work is greater than 0. Work is greater than 0, which is positive. But if it is getting out of the system, we are subtracting negative W. You look at here, work is done by the system. Please, there is this means work is done on the system, and this is work is done by the system. These are the terms you will see in the exam, and if you don't understand, it will be very difficult for you. So that if you are asked to calculate change in internal energy, you will use this equation, or if I give you this index, all you have to do is plug in this, plug in that, and depending on the sign for here, all right? Here means heat is given off by the system. This means absorbed, all right? It is absorbed from the surrounding. It is absorbed from the surrounding. Here it is, so, if I blow up this, you may not really understand if given here, because they expect you from math class when we have this notation, what means it's greater than 0. Greater than 0, greater than 0. Look at the arrows where it's going, okay? There are more information conveyed by the notation on this slide, which will make our life easier in the subsequent step, all right? Remember here, the units have to be the same. They have to be the same. So with respect to the system, change in internal energy Q, which is a symbol for heat and work, you need to know the sign convention. You need to memorize. You need to have it in your fingertips before exam, before the quiz, that for positive Q, that means the system is gaining heat. Look at this. Positive, it's getting into the system. Minus means system is losing. So here negative Q means the system is losing. The arrows indicates where the heat is going. For W, that is what positive W means work is done on the system. See here, positive means work is getting into the system. It could be due to compression, all right? If it contracts, those are the terminologies you see with respect to work done on the system. And when it is expanding, that means it's going out. This could be expansion. Work is doing, or the system is doing work. The system is doing work, or work is being done on the environment, or work is being done on the surrounding. With this, remember now energy cannot be created or destroyed. So whatever we had it in the system, it is lost into the surrounding, but we don't really destroy. It's just go somewhere else. Whatever is coming in from the surrounding, all right, into the system, it's not lost, but it's just being transformed at the region of the universe. So basically, we can say from the second law, all right, from the second law of, from the first law of thermodynamics, the energy of the universe is constant, right? Now, this is just to illustrate exothermic endothermic reaction. So if for Q, negative Q, this is given off, and it is for what we say exothermic reaction, a reaction which gives away heat, all right? A reaction which gives away heat is exothermic, but positive Q, it is absorbed, right? Absorbed, that means from the surrounding. We absorb it from the surrounding. We call this endothermic reaction. Endothermic reaction. I'll use the word exo and end to remember exit, to exit, exit, go away, enter, getting in. So if you look at the temperature here, I just to blow this at room temperature before you add or you mix the two reagents here, the temperature is around 23 degrees Celsius, but upon mixing the two reagents, the temperature went all the way to negative. That means, all right, that means it is endothermic reaction. If the temperature is going down, it is endothermic, which means why I know it's kind of like confusing what is going on. It means if it is endothermic, if it is negative, if before I put anything in my cup here, I hope you can see my UNF cup, if that is my reaction flask, or even I can have a better one. Let's see. Yeah, so this is a reaction flask. All right, if it is endothermic and I hold it, if it is negative, that means it will absorb heat from my hand. I will feel it. It is cold, ice cold. Why? It's because the temperature is lower than my body temperature. Therefore, if I measure with the thermometer, I'll see it as negative. For exothermic, such as thermite reaction. Is this thermite reaction? No, it's not a thermite reaction. This is just reaction between potassium and liquid H2O. The potassium readily react with H2O. This is exothermic. It gives away heat. And this we expect the temperature to go up. If you were to measure up, that temperature will, all right, we'll see the temperature going up. So remember exothermic, endothermic reaction, giving away heat and absorbing heat from the surrounding, observing heat from the surrounding. I want us to look at something what we call state function, and what we mean by state function, all right? State function All right, here let's define what we mean by state function. State function like that. All right, state function are properties or property of a system. A state function is a property of a system that is determined by specifying condition of the system. All right, condition of the system. Unless you specify the condition of the system, there is no way you will know. It only depends on the final and the initial, all right? On the final and the initial state of the system. A property of a system that is determined by specifying the system condition, okay? We have no way of knowing the internal energy of the system. It's too complex. So internal energy is one of the state function, because there is no way we can know that unless we specify that. This illustration here, okay, the diagram or this illustration here, this is 50 grams of H2O, liquid H2O, at 25 degrees Celsius. All right. To get to this condition, we don't know. You know, there are so many ways we can. Get to this state. We can either melt 50 grams of ice at 0 degrees Celsius, or we can cool 50 grams of H2 at 100 degrees Celsius to 25 degrees cold temperature state. It's a state function. It only depends on the current condition. Okay, so it's not something we can know. So therefore, internal energy is a state function. So here, E state, what is a state function? I've seen, and you may see in the quizzes or exam, stating whether internal energy is a state function, whether work is a state function. Gonna see that down the line. But remember, internal energy of the system is a state function. It only depends on the present state of the system, not the path by which it arrived there. Read more. There are so many examples in the text on how to illustrate the state function. I would want to shift gears to section 5.3, which is enthalpy. 5.3, section 5.3. This is enthalpy. And what is enthalpy? This is the first time you're looking for enthalpy. All right, enthalpy. This is a Greek, all right, Greek term, which means enthalpy. It means this is I. Enthalpy, it means enthalpy. meaning an heat, just heat. All right, enthalpy. So enthalpy of reaction is simply heat of reaction, denoted by this, denoted by letter H. We use this H, enthalpy or heat. So if we say enthalpy, enthalpy is to understand how this one works. Enthalpy of reaction, all right, is simply heat of a reaction, heat of reaction, which we can write H, Rxn means heat of reaction, heat of reaction. The subscript here, Rxn, is heat of reaction. So enthalpy of reaction, and this means when we have here delta H means change in enthalpy of reaction, change in enthalpy of reaction. Gonna have that change in enthalpy of reaction. So it means enthalpy means to warm or to heat. Now, if a process takes place at constant pressure, and we usually work at atmospheric pressure, always, all right, always we work or always pressure. It's gonna be pressure in ATM. ATM is atmospheres. ATM is atmospheres, all right? Only work done is the pressure PV work. We'll see pressure volume work. We can account for heat flow during the process by measuring enthalpy of the system. And you know now what the system is. We'll see how to do that and how to determine the PV work. And the level of is internal energy plus the product of pressure volume work. So here, this is internal energy and this is the volume. What comes or what you should pay attention is this volume can be changing. It's changing volume so that when we have compression, let's look at this first. Let's look at this volume here and pressure, okay? Pressure volume work, we call it PV work, all right? Pressure volume work can be either through compression or expansion, all right? Expansion. Through compression or expansion. This is associated with what? Volume changes. In this case, if this is the initial, if this is the final, we know that there is expansion. V final is, all right, I should have it here, that compression here, V final is less than V initial. Whereas here, V final is greater than V. This is V what? This is V initial, V initial that, okay? V initial, expansion and compression. So that here, delta V means change in volume. So on, V, this is change in what? Change in volume. And in BV work here, we determine change in volume. Change in volume is given by V final, always have the initial minus V initial. And remember, the unit has to be the same. If it is in liters, got to be liters. If it is in ml, change to liters. When you have it, in different, for a reason, I'm going to show you why volume has to be in liters. Okay, so here change in volume is determined by taking the final or subtracting the initial from the final volume. All right, final volume. Always have volume in liters. This is just an example of what happened when this is our system and there's some sink here, there is HCl, and when you twist this, the sink metal will react with HCl, releasing for single replacement reaction, releasing hydrogen gas. And if you look at the piston, this is the initial position. There will be expansion. PV work is being done, or the system. This is the system is doing work on the piston through expansion. You see here, expansion is expanding. I don't have the contraction, but we expect the volume to reduce for that. There will be calculation. Let me just give you a heads up that you will do the calculation. And this is the equation, PV work, all right? For PV work, that means you'll calculate work is always given by negative, is always there, pressure times change in volume. Note, all right? Note pressure always in ATM, should be in atmospheres. I know you covered, or we will look at, if you didn't cover, it's expected that you covered in introduction to chemistry. If you took introduction to chemistry, Car's laws, and learn how to convert pressure in one unit to the other unit using the conversion, appropriate conversion. And volume in liters, always volume in liters. If this is negative, if change in volume is negative, remember here, you have to have V final minus V initial. If you end up with a negative here, negative times negative turn out to be positive, which means it's compressing. The system is compressing. Work is being done on the system. Remember the sign convention. And go wrong with that. So I will use, or this is the equation. You need to remember how to use in order to calculate the work done. Now, if you multiply that, the units will be in liters times atmospheres, because the pressure is in atmospheres, the volume is in liters, and to reconcile with the units, 1 joule, all right, equals to 101.3 liters times atmosphere. You will need this to convert now to what? To joules. To joules. Maybe I'll give you this in the exam, but remember, when you'll be doing the MyLab and mastering assignment, you may need to have this conversion factor so that you express the work in joules. Once you get your value in liters times atmosphere from this equation, you'll end up with the units in liters times atmosphere. And then you will now have, let's say you have yourself x liters times atmosphere. Let's say this is your answer from the assignment. Use the conversion factor given here that 1 liter times atmosphere equals to 101.3 no, this is joules. I'm sorry, this should be joules right here. And this should be liters times atmosphere. So that liters times atmosphere will cancel with that, and you express yourself the correct one. Work done by the system, work done on the system, all right, with the correct unit in joules, all right, yeah, joules like that. Perhaps maybe solving an example, all right, perhaps solving an example will help you see how you use that equation. How you use that equation will help you. Looking for my notes here, all right, that I need my calculator to be ready. Okay, you should have your calculator, learn how to use this. In the exam, you will use the Honor log. Okay, you'll use the Honor log. Now, look at this, calculate the work in joules. All right. If the volume of a system contracts from 1.55 liters to 0.85 liters at a constant pressure of 0.9. So we know here is the solution. So I have what? Work is given by PV, changing volume. Let's break down. Pressure is 0.985. V, or change in volume, is given by V final minus V initial, which is 0.85 liters, all right? Minus 1.55, which is equals to 0.7. This is 0. Not 0.0, so series 0.7 liters. This is the negative, by the way, negative 0.7 liters, negative 0.7 liters. So if I want to, okay, change that, it will be change in, rather, W here, work, given by change in times change in volume. This is negative 0.985 ATM atmospheres, all right, times negative 0.7 liters, and here is 0.0. So if I have that on my calculator, 0.985 times 0.7, I have 0.6, all right, 0.6895. This is liters times atmosphere. And remember, the question is in joules. So we need to change that to joules. 0.6895 liters times atmosphere. Remember our conversion factor, right? You'll be given this conversion factor here. right here. 1 liter times atmosphere equals to 101.3 joules. So it's going to be what? 101.3 joules 1 liter times atmosphere. So that atmosphere and atmosphere goes liter and liter we call. You see how I'm changing to joules from the liters times atmospheres to joules, and this will be 69.8 joules. And if I round up that, it will be to 70.8 to make it too significant. If I round up, that's gonna be 10, and then you just carry out that. This is joules. This is how you will end up with what? The answer in joules. Please do more practice on PV work. Okay, this conversion factor here you will see in the next exam, the next quiz. Okay, so make sure you do it. Make sure you practice with it. All right. So now let's see now, having seen the PV work in terms of, we have seen the PV work, remember change in enthalpy equals to change in internal energy plus BV. We have seen this term, the BV work. So that is the change in internal energy, change in, this is change in and here is change in changing energy, changing internal energy of the system. We can calculate that. Now at constant pressure, all right, at constant pressure, change in enthalpy is just considered as H. At constant pressure, change in enthalpy for reaction is just the same as Q. And remember, this is heat. All right, remember what we said earlier on, Q is negative. I will not require you to, at this point, to derive the equation to show that Q equals to change in what? Change in enthalpy for reaction. This is the heat of reaction. This is just the same thing, which we know from earlier on Kane. So at constant pressure, this is what I'm just at constant pressure, the change in enthalpy is either heat loss or heat gain. Heat loss by what? By the system. So if here is the system, you say heat gained, which is what? Endothermic reaction. Endothermic reaction. And then negative, this means negative Q heat lost, and this is exothermic reaction, exothermic reaction. So you have to know what is meant by gain or loss. It is with respect to system. It's respect to where the reaction are. A plus B going to C plus D. Going to C plus D. If we reconcile now Q with this and delta H here, all right, look at this. Look at this. This means delta H equals to positive for here. Here, delta H negative. For these guys right here. You need to remember that the negative value for delta H or enthalpy change in enthalpy reaction for negative is exothermic reaction Q for that. So we will reconcile with the numerical values. Down the line, we'll reconcile with the numerical values for exothermic endothermic reaction. Remember, giving heat endothermic reaction. This is an exothermic reaction. We're gonna have that. A process is endothermic when delta H is positive. Look at this, delta H is positive. A process is exothermic when the heat is negative. So look at this, anything greater than 0 is positive. So it's getting in there. You know, when you say positive, somebody might think that, okay, we are removing our, however you look at it, please understand what this symbol means. Anything greater than 0 is positive from the number line. Remember, from the number line, 0, 1, 2, 3, -1, -2. So anything greater than 0 is positive. Anything less than 0 is negative. This is positive for exothermic and endothermic. Let's see learning check here. When a reaction in a flask, you notice that the flask gets cold. What is the sign? It's getting cold, right? If this is my reaction flask again, and I hold it, all right? This is my flask. It's getting cold. Do you expect the value for change in enthalpy for reaction to be positive or negative? It is positive, all right? If you guess it to be positive, that is right. Because of what? The system is absorbing heat because of when I hold it, it is absorbing heat from my hand and then I feel it's cold. It's getting or drawing heat from my hand into the system. Therefore, I feel it cold. If it was negative, that means giving away heat. I will feel it. It is warm. It is hard. Like I feel like dropping. Then it will have been negative. Of course, C is wrong. So please do that. It's another example on critical thinking, chemical reaction that gives off heat to the surrounding is said to be a dash, giving away to the surrounding. It is exothermic reaction, and giving away heat to Israel is said to be and has a dash value. This is negative value, negative, exothermic, exothermic, negative. So the correct answer is D, exo, because it is giving away a chemical reaction that gives off heat to its surrounding. That means heat is getting out and the enthalpy of reaction is a negative. Without understanding of this diagram on the whiteboard, some of you, or you may find it, this problem challenging, okay? Challenging. Now, please make your own notes again so that, you know, wherever you are given problems on conception, on exothermic, endothermic, and the level of reaction and so forth, you'll be able to answer without any problem. All right, let's see enthalpies of reaction. We just have looked at the enthalpy by itself, but enthalpy of a reaction, chemical reaction. All right, when we say reaction. That means we have the products, we have the reagents. This means change in enthalpy. H, this is change in enthalpy, change in enthalpy. And if I put here Rxn of reaction, all right, it is obtained by H products all right, so product minus what reagent. Forget about the, this diagram that is just an illustration that if we are starting with the combustion of methane to form carbon dioxide and the liquid H2O balanced equation, if this is the reagent and these are the product minus reagent, we end up with a negative. You see how much it is given off in kilojoules, all right? But if we are combining these to give this, it's positive that we need. It's just illustration of enthalpies for reaction. We reverse the equation, the sign will change later on. Let's see, this quantity, the enthalpy of reaction is called, this is called enthalpy of reaction or charged heat of reaction. Remember what I defined earlier on, that enthalpy for reaction mean also heat reaction is the same as heat of reaction, like that. We have the reaction. H2O is formed when hydrogen gas, 2 moles of hydrogen gas react with 1 mole of hydrogen gas to produce 2 moles of H2O. Illustrate this. Anything less than 0 is negative. That means heat is given off. It's highly exothermic heat of reaction. There are 3 or rather even 4 properties of enthalpy. All right, it is an extensive property. What do we mean by extensive? That means this depends on the amount of what? Amount of reagents. You may want to say reagents or reactants. This means the more, remember extensive property, intensive property. Extensive properties are those properties which depends on the amount of matter present. So enthalpy or heat of reaction of course depend on the amount. Okay. If you have a large amount of hydrogen gas, oxygen gas to form liquid H2O, the more you have the reagent, the more heat energy will be given off for exothermic reaction. So remember, it depends on how much of the reagents you have. And the level of reaction is equal in magnitude, but opposite in sign if it is reversed. I think we had a couple of examples of reversible reaction. For example, here, right? Look at this. This is forward reaction. It gives away heat, but reverse reaction, they have equal work. So remember, if you reverse the equation, what we mean by that is if we have CH4, right? CH4, this is in gaseous state, plus 2 moles of oxygen gas to form CO2 gas plus 2 moles of liquid H2O. and the level for reaction in this case is negative 890 kilojoules. So if this is one of the, that is the equation, let's reverse the equation. If we reverse that, look at what the sign, this is gas plus 2 moles of H2O to form methane gas, CH4 gas plus 2O2 gas, like that. Delta and the level for this will be 890 kilojoules. So they have opposite. If we reverse the equation, okay, if we reverse the equation here, the sign changes. We have changed the sign here. Look at what is being referred to here. This concept, the first one, extensive property, reversing, this is the second property. We will use this concept down the line. Now, the enthalpy of reaction depends on the states of the reaction. States could be and by the end products, like that, products. So it's not only the reagent. Is it solid? For S, is it liquid? For L, gas, G, or aqueous. Remember how to interpret a chemical reaction? These are the physical state. So enthalpy of reaction, we can have CO2 in solid state, we can have CO2 in gaseous state, and the enthalpy of reaction for that are different. So we have to pay attention to that. Now, the last one I want to bring to you, which is not mentioned here, is when you multiply by a coefficient, you also multiply the enthalpy for reaction by that coefficient. If you divide the enthalpy for reaction by that coefficient. So here, what effect do these changes have on change in enthalpy for a reaction? Change in, that is multiplying by a coefficient of 2. The value doubles. So if I have, for example, I'm just gonna give you that, 2 moles of hydrogen gas plus oxygen gas to form 2 moles of H2O, like that. If let's say enthalpy for reaction here is negative 890 kilojoules, the one we were given. If we multiply by 2, that means 4 H2O, 4 moles of hydrogen gas plus 2 moles of oxygen gas going to 4 moles of liquid H2O. This will be, or delta H will be negative 2 times, or rather 2 times negative 890 kilojoules. You have to multiply by 2, which means the correct answer here is that the value of change in enthalpy for reaction doubles. If we divide by 2, it will do what? It will reduce by a half. It will reduce by a half. We will need this concept when we get to Hess's law, section 5.6. So remember that. All right. So far, what you didn't understand, or I need you to understand at this point, is when a chemical reaction or chemical equation is presented in this form, including the change in enthalpy for reaction, such as the one on the whiteboard and this one, we call this equation what we call thermochemical equations. That means it has the heat energy as part of the reaction. Now calculate the quantity of heat released when 5.00 grams of hydrogen peroxide decomposes at constant pressure. How to interpret thermochemical equation is based on the stoichiometry coefficient in the balanced equation. Here we read as when 2 moles of hydrogen peroxide decompose, it will release this amount of energy, kilojoules. When a half of this decompose to produce, this should be H2O, by the way. Sorry about that. This should be H2O. All right. So this should be 2H2O2 going to 2H2O plus oxygen gas. Let's see. Yeah, this is 4. This is 4. This is 4. Yes, and it's liquid here. This is liquid, and that is gas. And here delta H is negative 196 kilojoules. This is chemical equation. So if I reduce this by a half, as we saw in the previous learning slide, this will also reduce by a half. It is an extensive property, which we talked about. So how will you determine that? You need to find the number of moles. So what I'll do is set up the, we're gonna set up the equation, all right? We're gonna set up the equation, but we need to find the molar mass. You need right now from chapter 3, stoichiometry, you should be able to convert from mole to mass, all right? Mass to mole. So here we need to convert 5 grams of hydrogen peroxide in order to use the thermochemical equation to find out how much heat is given off. So I'm just going to write here, this is the solution. Solution for this is 5, all right? Look at what I'm doing, 0 grams of hydrogen peroxide, all right, times the molar mass of hydrogen peroxide, okay? The molar mass of hydrogen peroxide. Using periodic table, 34, if not given, use periodic table. 1 mole of what? 1 mole of hydrogen peroxide. This is from the what? Molar. If you are not given, use periodic what? Periodic table. I'm gonna use the periodic table. Times all right. Now we will use the thermochemical equation to relate the reactant and the amount of heat. From here, we know 2 moles of hydrogen peroxide will give away 196 kilojoules. Look at unit reconciliation. This will go away with that. All right. Maybe a different color this time brown, so that you get that. That will go away. And then when you multiply everything, I'm just gonna multiply this by 1 pi 196. Write it down if you're not sure of your calculator. Divide by 34.02 times 2, and you should have negative 24 kilojoules. I'm having express your answer three significant figures. Three significant figures. Because of three significant figures here. Why not 5.0? Why not 5? Why not 5.00? Because of the three significant figures have three significant figures in joules. So this is how you use the thermochemical equation to calculate the amount of heat energy given off for exothermic reaction. It could be endothermic reaction if it is positive, but nevertheless, you use the same approach. You use the same approach, okay? All right, let's shift gears. I'll recommend that do more problems. Don't just rely on the PowerPoint slide, expecting that you will do well in a quiz or ace the homework assignment. Go at the back of the text, end of chapter problems, odd numbered problems, or some problems you have what you have answers. Odd numbered problems you have answers at the back of the book. That's what I'll do on solving problems for practice. Let's move on to dive on to 5.4, all right, which is 5.4 is on this is a calorimetry, all right. What is calorimetry? This is should be what this is only one TR. I meant to say TR. Okay, calorimetry is the process by which change in enthalpy of reaction is determined in the lab, and you use what we call coffee cup at constant pressure. Coffee cup is used to measure enthalpy of reaction. This is an insulated coffee cup, and reason being, you don't want to, when you hold it with your hand, heat can either be lost or heat can either be absorbed. So we want the system to be isolated if need be. Remember the three systems? This needs to be isolated. It is equipped with either you will use magnetic stirrer in the lab, or you may have used magnetic stirrer to equilibrate, to make the temperature uniform. If reaction is exothermic, we expect the temperature to increase. Initial, final. Final will be greater than initial for exothermic. We mix two reagents, giving away heat, the temperature will rise. If we mix two reagents for endothermic, the temperature will come down, okay? Understand how this works. So in calorimetry, we determine the enthalpy of reaction by recording the temperature of the reaction. We call this calorimeter, and the process by which this is determined enthalpy of reaction is calorimetry. There are two, there are two terms you need to be able to define in calorimetry. First of all, heat capacity, denoted using C, all right? I'll define this as amount of heat energy required raise temperature, right? Temperature of a substance by 1 Kelvin or 1 degree Celsius. We don't specify the amount of substance. Just if I have 10 grams of H2O, or 50 grams of H2O, so long as I can change the temperature of both samples by 1 degree. Talk about the heat capacity. The units, I've seen problems asking you the units. This is given by degrees, no, joules per degree Celsius. Joules per degree Celsius. These are the units for unit is joules per. On the other side, heat capacity specific heat capacity, specific heat capacity, denoted C and then small s, I guess for specific. All right, look at how you define this. This is the amount of what? Amount of heat energy, just gonna be specific, heat energy required, all right, required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. This is joules. This is the units, grams times degrees Celsius. These are the units. So you should be able to define the heat capacity. We don't specify the amount of substance in defining the heat capacity so long as we can raise by 1 degree Celsius. But in specific, we specify the amount and look at the units so that we will be able to determine the heat given. Other than that, we have what we call molar, which is actually we are working with 1 mole of a substance. We call it molar heat capacity or specific molar heat capacity. Okay, is the amount of heat required to change 1 mole of substance. Here are a few examples of some substances with their specific heat. Look at the units, joules per gram per, this is times Kelvin. Change in 1 Kelvin is the same as change in 1 degree Celsius. I like using degree Celsius because when you measure the temperature of substances in the lab, we use a thermometer, and a thermometer, of course, measures the temperature in what? In degrees Celsius. We'll see later on why this one is useful, versus using the what? The Kelvin. Most substance we'll be working with in the lab is H2O, and specific heat is 4.18 times 4.18. So for H2O, all right, H2O, I'll say CS, which is a specific. Look at this, specific heat is 4.18 joules per grams times degrees Celsius. I'm just gonna read that. You don't need to worry about memorizing this. I'll give you specific heat of a substance if need be, all right, but know how to use. When doing the homework, you may need to flip the text not given in calculation, all right? I'll show you how you use the specific heat to determine the heat of reaction, the specific heat for reaction. Look at the specific heat for H2, or maybe just had for there, 0.18 or 0.184 doesn't make any much difference. There is an equation here. If we have two reagents, let's say HCl in neutralization reaction plus sodium hydroxide aqueous to form H2O sodium chloride, which is an ionic compound, aqueous, soluble in water. Solution is the combine. I've seen before or in the lab, for most lab report students get confused. You're mixing two things to form a solution. HCl in this case plus sodium hydroxide give us the solution here. Solute plus the solvent, which we'll see later on, solute equals to solvent, what you are dissolving in, plus the solute give us the solution. So you are combining two things here. Understand that this is two things. This is a specific heat. This is a mass. Q for the reaction. This is heat of reaction in joules is given by the mass. This is the mass in grams times CS, which stands for specific. You'll be given this unless you are asked to calculate specific. And this is joules per degrees times grams. And then times what? Times this. This is something new. All right. This is something new. This is change in what? This is change in temperature. Change in temperature. On this slide, this is change in what? Change in temperature. Change in temperature, which is determined by T final minus T initial minus T initial. Final minus initial. You see this? Delta means change in temperature. If you know the starting temperature, that is the initial temperature, and the final after the reaction, final temperature minus initial temperature gives you this term in this equation when calculating the heat given in joules. This is in joules. It's going to be in joules. And of course, if you want to change to kilojoules, then you use appropriate conversion factor. It's important to know, how to use this equation. All right. I'll give you that. You need to know how to change that in order to calculate the heat given off or the heat, all right, absorbed during a chemical reaction at constant pressure. Use the calorimetry. Let's see, using the equation on the whiteboard here to find the heat given off. Let's see this. The specific heat of octane is gasoline. Yes. Octane from 8 carbon chain. In liquid form is 2.22 joules per gram per Kelvin. How many joules of heat are needed to raise the temperature of 8 grams of octane from 10.0 degrees Celsius to 25.0 degrees Celsius? So how many joules? We will need this equation solution. Q, all right, for the reaction is given by the mass times CS times change in temperature. Do we know the mass of the solution? Yes, we have the mass of the solution. It's 8.0. I should have it here so that I have enough space. 80 grams of C8H18. This is the mass times the specific heat. Remember, it's given in joules, 2.22 joules per gram times degree Celsius. I'm just going to use degree Celsius times what? Change in temperature. 25 minus 10 is 15.0 degrees Celsius. Look at the units in terms of here we have grams. No, time is mass. Mass, grams and grams, we cancel that. So mass times specific heat, and then we remain with joules. So if we plug in that on the calculation, all right, and the calculation, you'll end up with this. Look at what your calculator may show. Joules. If you look at, I don't want you, if it's online or if it is a quiz, you just settle on what you see on your calculator. This is more than what we need. You should express with the correct number of significant figures. Always, if you look at the multiple choice, once everything is done, round off to the correct number of significant figures. Here, 10.0, 3 significant figures, 2.22, 3 significant 8. So everything has to be in 3 significant figures. Don't round off to 266, but just a placeholder, 2660 joules, or 2.66 times 10 raised to 3 joules. I'll go with this. Always double check so that you don't bubble the wrong multiple choice. If it was an exam, you may have this, which is more than the required number of significant figures. Quite often student means easy problems, not because they don't know, not because they didn't use the correct equation, because of just bubbling the wrong choice, forgetting that we play with the rules of significant figures. So remember that. That was the determination of enthalpy of reaction at constant pressure. We use calorimeter in a process called calorimetry. It's a process by which you determine the enthalpy of reaction. We can measure the internal energy of the system using what we call the combustion, using what we call the pump calorimetry. Is a process by which you determine the internal energy of the system. We need to know the heat capacity of the calorimeter and what? The change in temperature, which is just final minus initial that. You'll see this in the lab where you'll be calculating the heat of reaction given the heat capacity of the calorimeter. The negative here is because either heat is, this is given up or release, absorb will always be negative. Just look at that. Let's look at this example on again. We will not look at the in details the pump calorimetry, but just to give you an overview of what's all about. Of interest is the calorimetry determination of heat of reaction at constant pressure. You will see this, you will perform in the lab. It's one of the experiment. I think it's experiment number 10 for those who are taking CHM 2045L at UNF. It is experiment number 10, heat of reaction. Let's see, still on the coffee cup calorimeter using this equation Q, all right? Remember Q for the reaction is given by mass times the specific, let me not use a specific, but write CS times the change in temperature, change in temperature. When a 6.50 grams of solid sodium hydroxide is dissolved in 100.0 grams of H2O in a coffee cup calorimeter, the temperature rises from 21.6 to 37.8 degrees Celsius. Calculate the temperature, calculate the heat in kilojoules released in the reaction. Using the heat, results from part A, calculate the enthalpy in kilojoules per mole sodium hydroxide. So the first part A, we will use this equation. And mass here, all right, mass is mass of NaOH plus mass of H2O. So we have two things because we're gonna have the solution. There is a mass of solid sodium hydroxide and a mass of liquid H2O. So here we have 106.50 gram. This is the mass of the solution. Since we are dissolving in H2O, making the solution water, we'll use the specific heat of H2O, which is 4.184 joules per gram times degrees Celsius times change in temperature, all right? Change in temperature is 16.2 degrees Celsius, so that degrees and degrees will go away, grams and grams will go away, and will remain with 67 if I multiply that. So let's see, this is 106.5 times 4.184 times 16.2. 16.2. This is 7218.655 2 joules. This is more than what we need. From the first number here, okay, 3 significant figures. If we divide by 1,000, it's gonna be 7.21. 1, 2, 3. I divide by 1,000. Somebody can say, how did you end up there? In kilojoules, if you want to know how we ended up with that, this will be rather in kilojoules. 1 kilojoule equals to 1,000 joules. So this will be 7218.6. This is joules. 1,000. So that will go away. We have 7.21 kilojoules, 3 significant figures, all right? Because of the 3 significant figures. This is the amount of heat quantity release. It's exothermic. It's exothermic reaction, so it's given off. All right, so that's how much it is given off. In part B, using the results from part A, calculate the enthalpy of reaction in kilojoules per mole. So we need to know how many moles of sodium hydroxide we have in 6.50. So we can change that number of moles of NaOH. You have to convert, first of all, the grams of NaOH using the molar mass as a conversion factor. Just approximate that. Please use the periodic table to find the number of moles. Grams and grams will go away, and we have 0.16, all right, 25 moles of NaOH, all right? So that is what? The number of moles. So in order to get the kilojoules per mole, the numerical value for A divided by the number of moles. Therefore, all right, delta H in kilojoules per mole is given by what? 7.2, so right, 7.2, all right, 1 kilojoules divided by 0.165, 1625, all right. This is moles, which is equals to negative 44. Yes, so if I have 7.8, this is 7.21 divided by 0.1625. It's negative, yeah, 36. It's given off. You see this? Given off means impure. So this is what is given off. All right. You remember to use the periodic table to find the molar mass of your compound. Now, if you recall in the previous chapter, naming of the organic compound, that's chapter 2, you should be able to write the correct formula for compounds. For example, here, sodium hydroxide. If I didn't know how to write the correct formula for sodium hydroxide, how will you determine the molar mass of sodium hydroxide? Using the periodic table, look for atomic mass of sodium plus atomic mass of oxygen plus atomic mass of hydrogen. So remember, if you don't have a solid foundation in some of these concept naming of the compounds, it's going to be very difficult. Okay, this is not the only one. We have many more coming down the line, and even it goes beyond Chem 1 that you need to know. I'm allowing you to use some of the material in the exam, but in the future, you may take somebody else who will not allow you, and they will expect you to have learned in general chemistry 1. Other than that, that's what you wanted to, or what you have to do for this problem. I will come back again for part, all right, for part B of this chapter 5. Please continue working on the homework assignment. Please catch up with studying, catch up with the homework assignment. Don't be left behind. Thank you and have a wonderful day.